All right, your next reading is sampling and estimation. End of chapter questions. Question number 1. Peter Biggs wants to know how growth managers performed last year. Biggs assumed that the population cross-sectional standard deviation of growth manager return is 6%. Okay. And that the returns are independent across managers. Fine. How large a random sample does Biggs need if he wants the standard deviation of the sample means to be 1%? This is basically the standard error of the sample mean. We know the formula. It's a very straightforward question. You just need to plug in the values and you will get your answer. So we need the standard deviation or the standard error of the sample mean as 1%. And this is not 6, remember, it's the standard deviation population, so it's 6% upon n. So simply take n on the other side, it's going to be 6% by 1%, taking the square on both the side, percentage sign would be cancelled. So basically you have under root n, 6 taking square gives you 36. So the random sample of n would give you the standard deviation of sample mean of 1%. You just need to plug in the formula, plug the numbers in the formula and get your results. So it's 36 and 36 it is. Next, same data, but this time what you need the standard deviation of the sample means to be 0.25. Right? Apply the same formula. Point 25% is equal to 6% upon n, which will be square root n is equal to 6 upon 0.25. It's going to be 24. And now squaring both sides will give you n is equal to 24 squared would give you 576. So that's your answer. The sample size is 576. The random sample of n 576. Next, Petra Munzi wants to know how value managers performed last year. Munzi estimates that the population cross-sectional standard deviation of value managers return is 4% and assumes that the returns are independent across managers. Munzi wants to build a 95% confidence interval for the mean return. How large a random sample does Munzi need if she wants the 95% confidence interval to have a total width of 1%? Now, this is interesting. We know 95% confidence interval would mean 1.96 standard deviation, positive side, and x minus 1.96 standard deviation, the mean. We want this width to be 1%, right? So that means you're talking about this whole region. So it's going to be x bar plus 1.96. This is the plus region. And since it's negative, so basically we are adding this negative number. So you need to put the negative sign, x bar minus 1.96 sample standard deviation is equal to 1%. Now if you simplify, they will be cancelled out. This negative sign will convert this 1.96 into positive. So you will have basically 2 times of 1.96 standard deviation sample mean is equal to 1%. So making Sx as the subject, what you get after the simplification, you get 0.255%. Right? What actually do we need? We need how large the random sample does Munzi need if she wants the 95% confidence interval to have the total width of 1%. So we have found out the sample standard deviation. Let us calculate the sample size using the standard error or sample mean. We have been given the standard deviation 4% here. N is to be calculated, and 0.255 has already been calculated just now. Making n the subject, if you make n the subject of this equation, you get 246. We need a sample size of 246 if she wants the 95% confidence interval to have a total width of 1%. So that makes 246 to be the correct option here. Next part related to the same scenario. Munzi expects a cost of about $10 to collect each observation. If she has a $1,000 budget, will she be able to construct the confidence interval she wants? In the previous question, she needs 246 observations. It costs $10 to collect one observation. So basically she needs $2,460 in order to achieve what she wants in the previous question. In the budget available, she can only $1,000 and $10 per observation. So she will only be able to collect 100 observations, which means that the budget is insufficient. What she should do? Now she can either proceed with her current budget and settle for 100 sample size, but for that she needs to have wider confidence interval, or she will have to raise her budget to $2,460 to get the sample size of 246 and achieve 1% width in her confidence interval. So it's all about the money, right? Next. Assume that the equity risk premium is normally distributed with a population mean of 6% and a population standard deviation of 18%. Okay, so that's your population standard deviation and the population mean. Okay. Over the last 4 years, equity returns relative to the risk-free rate have averaged negative 2%. You have a large client who is very upset and claims that the results this poor should never occur. Evaluate your client's concerns. In A, construct a 95% confidence interval around the population mean for a sample of 4 years return. Okay, since we are talking about 95% confidence interval, so basically it's going to be for the critical Z value of 1.96 on both sides of the normal distribution. So it's going to be, this is going to be your lower limit, 1.96 times population standard deviation upon the sample size, and the upper limit 1.96 standard deviation time the sample size. Now simply replace the values. 6% into 1.96 times 18%, square root of 4, n is 4, it's 2. So when you simplify this all, it will give you negative 11.64%. Do the same thing, 6% plus 1.96 times 18% upon 2, it would give you 23.64%. Now what does it mean, positive? It means there is 95% probability that the 4 years average return will be between the lower limit of 11.64% and the upper limit of 23.64%. Right, next. Same situation, same scenario, part B. What is the probability of a negative 2% or lower average return over a 4-year period? Well, for this, what we will do, we need to first find the critical z value associated with negative 2. How do we do that? I hope you know the formula. Z is equal to mean. Simply replace the values. If you do, it's negative 2% minus 6% upon 18% upon 4. And it simplifies to negative 8% in the numerator and 9% in the denominator. And finally, it gives you negative 0.89. So there are two ways to do it. The quickest way is to just look it up in the negative z-scores table, and you will find that the probability corresponding to negative 0.89 is 18.67%. So what this percentage tells us? It tells us that a 4 years average return of minus 2% or lower should occur 18.67% of the time. All right, next. Next is compare the standard normal distribution and the student's t distribution. Okay. First, there is only one standard normal distribution for a given set of data. But many t distributions exist, one for every different number of degree of freedom. The normal distribution and the t distribution for large number of degrees of freedom, they are practically the same. Third, normal distribution has thin tails, whereas the t distribution has fatter tails and lesser data in the center. And there can be others. I hope you would have gone through your reading related to this specific topic. So moving on. Okay. Next, question number 5. Find the reliability factors based on the t distribution for the following confidence intervals for the population mean. DF stands for degree of freedom and N sample size. For A, 99% confidence interval and a degree of freedom 20. So remember, for a 99% confidence interval, the reliability factor we use is 0.005. So let us look it up in the t table. So here we are for 99% confidence interval, that is 1% divided by 2, that is 0.005, and the degree of freedom is 20. So if you just come down the column, and these are the degree of freedoms given, so it's 2.845. So for 90%, it's going to be 90% confidence interval, degree of freedom 20. So it's going to be 10% upon 2, that is T 0.05. Let's look it up in the table. All right, here we go. And it's 1.725. 1.725. All right, next, a 95% confidence interval and N is 25. Remember, the degree of freedom is equal to N minus 1. It's going to be 25 minus 1, that is 24. So basically, what we are going to go for, at 95 confidence interval, T is going to be 5% upon 2, that is 0.025. And look that up against the degree of freedom of 24 in the T table. So here we are, 0.025 right in front of the degree of freedom 24. It's 2.064. 2.064. And last, at 95% confidence interval, n16. n16 means the degree of freedom will be n minus 1, 16 minus 1, that is 15. And at 95% confidence interval, t is again the same. And just let's look that up in t table. So we are right here, coming down the column. This is the one, 2.131. 2.131, and they will all match with the numbers given at the end, as you can see. Next, assume that monthly returns are normally distributed with mean of 1%, okay, and a sample standard deviation of 4%, okay. The population standard deviation is unknown. No. Since the population standard deviation is unknown, and we have to construct a 95% confidence interval for the sample means of monthly returns with a sample size of 24 only. Now, since the sample size is small and we do not have the population standard deviation, so we will have to use the t distribution to solve this question. For that, what we do, take the point estimate plus minus in order to develop the confidence interval, t alpha by 2 s upon n. So mean is 1% plus minus, since it's on 95% confidence interval, so it's going to be 5, but that's 0.025, s 4%, n 24. Now, if n is 24, then that means degree of freedom would be n minus 1, that is 24 minus 1, 23. So what you're going to do, go to t table, okay, upper tail 0.025 at 23, 2.069, 2.069. All right, so it's going to be 1% plus minus 2.069 times 4% upon square root of 24. So if we simplify this part of the arrangement, what we get is 1.69, right? So the confidence interval would be 1% minus 1.69% to 1% plus 1.69%. So it's going to be negative 0.69% and 2.69%. What does this tell us? It tells us that the 95% confidence interval spans the range from 0.69 to 2.69. All right, next question. 10 analysts have given the following fiscal year earnings forecast for a stock: 1.40 by one analyst, 1.43 by one, this earning forecast by 3, 2 analysts, this forecast by 1, 1 and 1. Because the sample is a small fraction of the number of analysts who follow the stock, assume that 10 analysts, remember, assume that we can ignore the finite population correction factor, assume that the analyst forecasts are normally distributed. So what are the mean, forecast and standard deviation of forecast? So it's fairly straightforward from your previous readings. What we will do, we'll construct a table representing these returns and the frequency. So these are the forecasts, returns, and this is the frequency. Now, multiplying the return with frequency, 1 and 1.4, all these numbers are here. Now we can calculate the mean, 14.5 based upon the 10 observations, 10 inputs, so it's going to be 1.45. Right, this is the mean. Now we need to calculate the variance. For this, first we need to calculate the deviations from the mean. 1.45, so 1.40 minus 1.45, 1.43 minus 1.45. So all these are the deviations from the mean. Deviation squared, and after squaring the deviation, multiplying with the frequency. This times this, this times this, this times this, and all this gathered gives you 0.0070. Right? Now we know how to calculate the standard deviation. We have the numerator divided by n minus 1, that is 10 minus 1, 9. This is what is the variance, and if you take the square root, 0.02789. This is the standard deviation of the data. So very fairly straightforward from your previous reading. So nothing unusual, nothing new. What is new is the next part. Provide a 95% confidence interval for the population mean of the forecast. So we have to establish the confidence interval. Remember, just sample size is 10. Population standard deviation is not known. Then we will have to use the t-distribution. And for that, we know what to do. Point estimate plus minus t alpha by 2 times standard deviation of the sample. What was mean? 1.45 plus minus. S we just calculated previously, 0.02789 upon square root of 10. Now for this we need to consult the t-table. Remember, 95% confidence interval means that reliability factor at 0.025 will need n is 10. So that means the degree of freedom would be n minus 1, that is 9. So let's see what we have in the t-table. T 0.025 at the degree of freedom 9 is 2.262. 2.262. Now if you simplify this part, it gives you plus minus 0.02%. Now we know. So the confidence interval will be 1.45 minus 0.02, that's 1.43, and 1.45% plus 0.02 means 1.47. So the confidence interval for the population mean ranges from 1.43 to 1.47. Right? Next. Similar question. 13 analysts have given the following fiscal year earnings forecast. These earnings, these many analysts. What do we need to do? What are the mean forecasts and the standard deviation? Will do the same thing. First you will calculate the mean, multiplying these, getting the results, adding them up, and then dividing by 13 gives you the mean. Then you calculate the deviations from the mean, deviation squared multiplied with the frequency and giving you this. This upon n minus 1 will give you sample variance, and then taking the square root will give you the sample standard deviation. Same thing we did in the previous question. Same data. What aspect of the data makes us uncomfortable about using t-tables to construct confidence interval for the population mean forecast? In the previous question, there was a slight difference. Assume the analyst forecasts are normally distributed. Sample size is less than 30, so we can use t-distribution. But here, no such assumption is given. Sample is small and the distribution is not normal. So we cannot compute a confidence interval for the population mean because we have probably sampled from a distribution that is not normal. That is not normal. That's what I just said a little while ago. So we can't do this. Moving on to question number 9. Explain the difference between constructing a confidence interval when using the normal population with the known population variance and sampling from a normal population with unknown variance. It's a fairly straightforward textbook based question. If the population variance is known, the confidence interval is calculated using z-distribution. We've done this previously. But if the population variance is not known, we will have to find some alternative. What we do then, we use the sample standard deviation instead, and the second is that we use the t-distribution instead of normal distribution. So this is what we have been doing so far, so nothing new. All right, the next question is, an exchange rate has a given expected future value and a standard deviation. Assuming that the exchange rate is normally distributed, what are the probabilities that the exchange rate will be at least 2 or 3 standard deviations away from the mean? First, 2 standard deviation away from the mean. And then, let's say just symbolic representation, 3 standard deviations away from the mean. What are we looking for? Of course, for the standard normal table or Z table. Going there straight. For 2 standard deviations, it's 0.97725. So since it's in 2 tails, it's going to be 1 minus 0.97725 multiplied by 2. It's 0.0455, or you can say it's 4.55%. Let's do the same for the second part. For 3 standard deviation from the mean, it's 0.99865. It's going to be 2 times of 1 minus 0.99865, and if you simplify this, it gives you quite a small number, 0.0027. If expressed in percentage, still small, 0.27%. Now there is a B part to it as well. An exchange rate has given expected future value and standard deviation. Assume that you do not know the distribution of exchange rates and use Chebyshev's inequality, that is at least 1 minus 1 k squared proportion of the observations fall within the k standard deviations of the mean, k standard deviation for any positive integer k greater than 1, to calculate the maximum probabilities that the exchange rate will be between 2 to 3 standard deviation away from its mean. So we can estimate using Chebyshev inequality k standard deviations would be less than 1 upon k squared. So let's apply k first, 2, and then k3. If you replace k with 2, what you get is 1 upon 4, that is 0.25. And if you replace it with 3, 1 upon 3, 1 upon 9, that will give you 0.111. Now just compare these probabilities with the previous numbers. See, 4.5% and 0.2%. And here it's 25% and 11.11. So you can see there's a huge difference. The probability of the rate being outside 2 and 3 standard deviation, the mean, is much smaller here than when the distribution is unknown and we are relying on Chebyshev inequality. So that's quite a large difference between these. All right, next. Although he knows security returns are not independent, a college makes the claim that because of the central limit theorem, if we diversify across a large number of investments, the portfolio standard deviation will eventually approach 0 as n becomes large. Is it correct? No. First, the conclusion on the limit of the 0 is wrong. Second, the support cited given here for drawing the conclusion that the central limit theorem is not relevant in this context. Diversifying into larger investments in larger portfolio doesn't mean the standard deviation will eventually reduce to 0. And even if, let's say if it does, it has nothing to do with the central limit theorem. What is the central limit theorem? Why is the central limit theorem important? I'm sure you have gone through the theory reading. In many instances, the distribution that describes the underlying population is not normal, or the distribution is not known. So the central limit theorem states that if the sample size is large, regardless of the shape of underlying population, the distribution of the sample mean is approximately normal. Therefore, even in these instances, we can still construct confidence interval and conduct test of inference as long as the sample size is large, generally, and is greater than 30. Right? Now, what is wrong with the following statement of central limit theorem? Central limit theorem: if the random variable x1 to xn are a random sample of size n from any distribution with finite mean mu and variance sigma square, then the distribution of x will be approximately normal with a standard deviation of sigma by square root of n. What is wrong with the statement? The statement makes the following mistakes. First, given the condition in the statement, the distribution of x bar will be approximately normal only for large sample size where n is greater than or equal to 30. Right? And the statement misses the important element of central limit theorem, that the distribution of x bar will have a mean equal to mu. Right? Next, suppose we take a random sample of 30 companies in an industry with 200 companies. We calculate the sample mean of the ratio of cash flows to the total debt for the prior year. We find this ratio is 23%. Subsequently, we learn that the population cash flow to the total debt ratio, taking account of all 200 companies, is 26%. What is the explanation for the discrepancy between sample mean of 23% and the population mean of 26%? Is it sample error? Yes. The discrepancy arises from sampling error. Sampling error exists whenever one fails to observe every element of the population, because a sample statistic can vary from sample to sample. As stated in the reading previously we done, the sample mean is an unbiased estimator, a consistent estimator, and an efficient estimator of the population mean. Although the sample mean is an unbiased estimator of the population mean, the expected value of the sample mean equals the population mean. That should happen. Because of the difference right here, you see, because of the sampling error, we do not expect the sample mean to exactly equal to the population mean in any one sample we may take. So that's clearly A is the right answer. It's a sampling error. Alcon Mutual Fund is placing large advertisements in several financial publications. The advertisements prominently display the return of 5 of Alcon's 30 funds for the past 1, 3, 5 and 10 years period. The results are indeed impressive, with all of the funds beating the major market indices and a few beating them by large margins. Is the Alcon family of funds superior to its competitors? Can we just assume because of these returns? No, we cannot say that Alcon Mutual Fund as a group is superior to competitors. Alcon Mutual Fund advertisement may easily mislead readers because the advertisement does not show the performance of all of its funds. In particular, Alcon Mutual Fund is engaging in sample selection bias by presenting the investment results from its best performing funds only. Next, Julius Spence has tested several predictive models in order to identify undervalued stocks. Spence used about 30 company-specific variables and 10 market-related variables to predict returns for about 5,000 North American and European stocks. He found that final model using 8 variables applied to telecommunication and computer stocks yields spectacular results. Spence wants you to use the model to select investments. Should you? And if you do, what steps would you take to evaluate the model? First, as we have seen in the given situation, Spence may be guilty of data mining. He has used so many possible combinations of variables on so many stocks. It is not surprising that he found some instances in which a model worked. In fact, it would have been more surprising if he had not found any. To decide whether to use his model, we should do 2 things. First, ask the model to be tested on out of sample data. on data outside the sample, outside the data population that you used, data that were not used in the building the model. The model may not be successful with out-of-sample data. Second, examine his model to make sure that the relationship in the model make economic sense. Right? The best approach of creating a stratified sampling of a population involves drawing an equal number of random sample from each subpopulation, not equal. Proportional, drawing simple population random samples from each subpopulation in size proportional to the relative size of each subpopulation. Perfect. Need no further reading. This is the right option. Next, a population has non-normal distribution with mean mu and variance. The sampling distribution sample mean computed from samples of large size from that population will have the same distribution as the population distribution. Wrong. How can the sample distribution be the same as population? Its mean approximately equal to the population. Correct. That's the textbook based question. B is the right answer. Next, a sample mean is computed from population with a variance of 2.45. The sample size is 40. The standard error of the sample mean is closest to. So fairly straightforward question. We have been doing questions like these previously as well. So it's going to be straightforward. Insert the numbers and you get your answer. Take the square root of this in order, because this is variance, so we need square root, and if we do, we get 2.45 square root gives you 1.565 upon 40, and it'll give you 0.247. That perfectly matches with your option B. Next, an estimator with an expected value equal to the parameter that is intended to estimate is described as a straightforward. It's a straightforward textbook-based question, unbiased. An unbiased estimator is the one for which the expected value equals the parameter it is intended to estimate. Next, if an estimator is consistent, an increase in sample size will increase what? Straightforward. Accuracy of the estimator. If an estimator is consistent, an increase in sample size will increase the accuracy of the estimator. Larger the sample size, the more accurate result you will get. For a two-sided confidence interval, an increase in the degree of confidence will result in what? A wider confidence interval. Again, a straightforward textbook-based question. As the degree of confidence increases, just like from 95% to 99%, a given confidence interval will become wider. Next, as the t distribution degrees of freedom decreases, the t distribution likely become, I hope you would remember, t distribution has fatter tails. As the t distribution degrees of freedom decrease, the t distribution will become even more fatter, exhibit tails that become fatter. As the degree of freedom increases, the fat tail ends become thinner. Again, a straightforward textbook-based question, no twist in it whatsoever. Next, for a sample size of 17 with a mean of 116.23 and a variance of 245.55, the width of 90% confidence interval using the appropriate t distribution is closest to. Fairly straightforward. We know what to do. Confidence interval is equal to point estimate plus minus t alpha by 2 times s upon n. We just need to plug in the right numbers. Do we have them? Yes, we have the mean 116.23, t alpha by 2. So you're talking about 90%, so it's going to be t 0.05 times s. What is s? Given right here. Square root of 245.55 will give you 15.670 upon square root of the variance, square root of the number sample size, that is 17. We need this. Since n is 17, so the degree of freedom is n minus 1, that is 17 minus 1, that is 16. So let's see what's the value there. 0.05 and the degree of freedom 16, 1.746. 1.746 times this plus minus this, what you get is 116.23 plus minus the solution of all this gives you 6.6357, which means your final interval would be 116 minus 6.6357 and plus 656, so it's going to be 109.59% to 122.86%. So that gives you what? So we are looking for the width. So if you just find the difference between these two, it will be approximately 13.271. That makes B to be the correct option. All right, next. For a sample size of 65 with a mean of 31 taken from a normally distributed population with a variance of 5 to 9, a 99% confidence interval for the population mean will have a lower limit closest to. Okay, since sample size is large, we can use the Z distribution here to determine the confidence interval. So it's going to be right. Do we have the numbers? Yes, we do. Mean is given as 31 minus standard deviation can be calculated by taking the square root of 529, and it's exactly 23, and square root of n, sorry, we should have put square root here, square root of 65. Now what you need to do at 99% confidence interval, at Z 0.005 at 99% confidence interval, the standard deviation is 2.58 times. So if you just simplify this all, it will give you 7.360 and 31%. Now since we need to give the lower one, so 31 minus 7.360, that is 23.64. So 23.64, the lower limit is perfectly matching with A. Next, an increase in sample size is most likely to result in what? If the sample size is increased, you will have a smaller confidence interval. Decrease in the standard error of the sample mean. Correct? Look no further. That is your right option, B. Next. A report on long-term stock returns focus exclusively on all currently publicly traded firms in an industry is most likely is prone to what you call the survivorship bias. Straightforward textbook-based question. A report that uses a current list of stocks doesn't account for firms that have failed, or they're out, or merged, or otherwise they've disappeared from the public equity market. So as a consequence, the report is biased because this contains only the companies that survives. It's a survivorship bias. Next, which sampling bias is most likely investigated with an out-of-sample test? Out-of-sample test, we just discussed it a little while ago. Data mining bias, this can be tested. If you just apply the model on out-of-sample test, then it will reveal that there's data mining bias. We just discussed this a little while ago, so that's a straightforward question, giving you B to be the correct option. Which of the following characteristics of an investment study most likely indicate time period bias? Time period bias, the study is based on short time series only, because a short time series is likely to give periodic specific results that may not reflect in the longer term. So look no further. This is the right option. That ends your reading, sampling, and the estimation.